Hello. Thus far, we have been talking about formal systems, but if you remember, Haugeland referred to computers as a kind of interpreted automatic formal system. Well, today we're going to talk about the interpretation aspect. We have also been using the adjective formal very frequently. We've talked about formal systems, formal rules, formal arrangements, etc. But what does formal mean anyway? Well, you must already have some idea, but it would be useful to be a little more explicit about it. What makes a system formal is that the specification of both tokens and rules is made without any appeal to the notion of meaning. Thus, what matters in a formal system is which configurations obtain, and not any relationship with the external world. Going back to our chess example, a checkmate occurs if and only if certain pieces are in certain positions with respect to each others, and absolutely nothing else matters. So, formal systems are entirely self-contained, and all of the moves and features are entirely definite. To give you an example, take this list of words. I'm going to mention two tasks that can be performed on this list, and you're going to say which one is formal in nature and which one is not formal. All right? The first task is to sort the items alphabetically. The second task is to classify the items in the list according to whether they are animate or inanimate. So, which task is formal? Well, clearly task 2 isn't formal, since to do it you have to know the meaning of the words on the list, and you have to know things about the world, such as which items can be living things and which are inanimate objects. You might have to consult dictionaries or, encyclopedias or books, or you have to Google things if there is something you don't know, or go out or do some observations on your own. Moreover, it will require some discretion on your part to decide whether Bender, which is a robot, is animate or inanimate, since a fictional robot. So this task isn't formal, since it depends on things about the world at large. It depends on matters of meaning, of content and understanding. Task 1, in contrast, only requires checking and comparing the shapes of the letters. So meaning doesn't enter into it at any stage. You might be dealing with meaningless words or arbitrary shapes, for that matter. That wouldn't change the nature of the task. So we know that formal systems, including computers, are only defined by means of formal rules, and that all of the aspects that determine its operation are formal. So from their perspective, if they have one, all tasks are of the same kind as task 1. However, what we call intelligence is associated with tasks of the second type, which require us to track features that bear on the world and to pay attention to meanings. But then there seems to be a problem in principle here, or at least a challenge, for the person who wants to design an intelligent formal system. The challenge is to create a system that matches a human's performance in 2, since that is what intelligence requires. But with the constraint that the system is in the end only going to be performing tasks like 1, since it is a formal system after all. Well, one of the things that this involves is what we are supposed to be discussing in this video, which is the interpretation of a formal system. Interpretation is concerned with the issue of meaning. So in this context, an interpretation is a systematic assignment of meanings to tokens in a system. And of course, by invoking meanings, we are entering the domain of semantics. Now, the word semantics is used in different ways in different contexts, and what is understood by it might be different depending on whether you are talking to a linguist or a philosopher or a computer scientist, just to mention a few possibilities. So just bear that in mind. Haugeland has a conception of semantics and of meaning that may differ from what you might find in other sources. Okay, back to our topic. Some, but not all, formal systems are lucky enough to get an interpretation. In this case, we say that their tokens have a denotation or reference, meaning that they stand for something. So chess, for instance, is a formal system that can be automated, but it is not an interpreted formal system. Outside of the rules of the game, the pieces have no intrinsic meaning, or at least you don't have to care about the meaning to be playing chess. An example of a formal system with which all of you are familiar is arithmetic, in which the numerals, which are the tokens you may write on the board or type on your computer, stand for what arithmetic is about, that is, numbers. Another system with which some of you may be familiar is propositional or sentence logic, in which uppercase letters stand for a proposition or sentences, depending on your preference. So when a token is interpreted, it is sometimes called a symbol. In the study of formal systems, semantics is usually contrasted with syntax. Syntax is a study of the formal configurations of the tokens of the system, so which ones are well formed, for instance. To use an English illustration, take Chomsky's famous example, colorless green ideas slap furiously. This is a perfectly well-formed English sentence, as you can see from the fact that it's perfectly parallel to sentence 2, which is obviously grammatical. However, it is a sentence which, at least when taken literally, can't be assigned a single coherent interpretation. I mean, think about it. Something that is colorless can't be green. And an idea is an inanimate entity that can be said to sleep. And finally, the idea of sleeping furiously, as opposed to, say, restlessly, is nonsense. So this sentence is semantically anomalous. And this is a case, then, in which syntax and semantics come apart. In the systems we are discussing right now, syntactic properties are formal. So this means that to determine syntactic facts, we need not go outside of the system. Some such facts, those syntactic facts, are determined by local factors. On the other hand, semantic properties, on the conception we are working with, are not formal. Not merely formal, at least. They are not self-contained, since they involve relations with the world. So, according to Haugeland, tokens of interpreted formal systems lead two parallel lives. On the one hand, they lead syntactical lives, in which they are meaningless markers, moved according to the rules of a self-contained system. But on the other, they live semantic lives, in which they have meanings and symbolic relations to the outside world. Now, since this is what makes formal systems interesting for us, then we must ask, how do the two lives keep in sync with each other? The answer comes in the form of what Haugeland calls the formalist motto, which says, if you take care of the syntax, the semantics will take care of itself. So algebra and logic, for instance, provide examples of this. Let's take an example involving logic, an inferential machine. Take this argument, 1. So the premise is that Al had ham and eggs. And the conclusion is that Al had eggs. Well, this argument is valid. It is impossible for 1 to be true and 2 to be false at the same time. So if the premise is true, then the conclusion has to be true as well. But then we have invoked the notion of truth, which is a semantic property. Thus, notions such as truth and validity are semantic properties. Now, let's consider a logic machine working on a formal language which we'll call Ogdenese. This is the syntax of Ogdenese. So on the top, we have the basic tokens composing its vocabulary, sort of asterisk, and then you have something that is like 4 diamonds, and then another symbol, which you're looking at. Then at the bottom, we have the definition, formal definition, of course, of a token of Ogdenese, or O token. So that symbol is an O token, that other symbol is an O token, and given any pair of O tokens, the result of writing the first token, writing that symbol, and writing the second token in that order is an O token. So here you have an example of a token of Ogdenese. And there we have more formal syntactic rules. In this case, there are rules for transforming some tokens into other tokens. So you have the rules 1 of 2 that says that if you have this string of symbols, then you might, if you want, detach one of these symbols. In one case, it is the star, in the other one, it is the 4 diamonds. So here's an Ogdenese machine at work. You have that as input, then you apply rule 2. If you have this, then write this, and then you have the output, which is just the rightmost symbol, just a detachment rule. So I know, well, this is not exactly mind-blowing, right? You ask, well, what is the relevance of this? Well, remember that this argument is valid, and that truth and validity are semantic properties. Now let's see if we can get some semantic mileage out of the syntactic engine of Ogdenese. To do so, first let's assign an interpretation to Ogdenese symbols. So this star is true if and only if Al had ham is true. That is, let us assume that that star stands for Al had ham. And then this other symbol is true if and only if Al had eggs is true, which is equivalent to saying that this other symbol is Ogdenese for Al had eggs. And then an interpretation rule for our concatenation symbol or conjunction symbol, which is that that sentence is true if and only if the leftmost symbol is true and the rightmost symbol is true. So that little symbol would be the equivalent of and, would be a conjunction. So it's only true if and only if the leftmost and the rightmost symbol are both true. All right. So the token, what does that token represent? Well, basically it represents Al had ham and Al had eggs. Note that there's nothing special about this interpretation, of course. It could have been a completely different interpretation. There's nothing intrinsic about it. It's just something that we are adding on top of it. Okay, this is what our automatic formal system, the Ogdenese machine, does. It takes that string as input, and then simply it applies rule 2, which is a detachment rule, which is that if you have that string, you can detach the rightmost symbol, and then you output it. That's all it does. It's just manipulating symbols according to their shape. But in virtue of doing this, it is doing things that make sense. It took as input, as a premise, Al had ham and eggs, and as output, it gave us a valid conclusion, which is that Al had eggs. So here you see the syntactic side, which is all that the machine is taking care of, is being kept in sync with the semantic side. So notice that the syntactic rules respects the semantic rule. So the detachment rule to the left basically respects the semantic rule that if you have A and B, then you can conclude B, for instance. And so that means that whenever the Ogdenese machine is given premises that are true as input, it will never yield conclusions that are false. In other words, the Ogdenese device will always reason validly, provided the subject matter is Al's breakfast, of course. So notice that the Ogdenese device only keeps track of the formal side of things. Its rules only appeal to the shapes and configurations of the tokens, so it is merely syntactic in the scope of its operations. However, by virtue of keeping track of a particular formal property, accordance to O syntax, it is also tracking a semantic property, such as truth. Hence, if you take care of Ogdenese syntax, its semantics will take care of itself. This leads us to an idea already floated in the 18th century by the philosopher, mathematician, and overall polymath Gottfried Wilhelm Leibniz. In order to build a machine that implements a logical calculus, or that performs arithmetical operations, he suggested the first step is to come up with a formal notation. We will define rules for manipulating the symbols in that notation. In a way, the rules of logic will allow us to deal with abstract ideas in terms of the concrete shapes of symbols. And so, by matching abstract ideas to concrete symbols, the manipulation and the propositional symbols will mirror relationships among the ideas that are being represented. And so the lesson then is that to produce meaningful answers, you don't have to understand what the symbols stand for or why the manipulations are correct. You just have a system that is set up so that mechanical manipulations purely defined over formal properties of symbols can only result in valid logical steps, thus respecting semantic properties such as truth or whichever meaning property you have in mind. So, to go to the heart of the classical computational theory of mind, we have to combine Hobbes' idea that thought is computation with Leibniz's idea of the formality of computation. And indeed, in the interpreted formal systems we have mentioned, such as arithmetic, algebra, propositional logic, and any programming language, the formal symbol manipulations are set out so as to preserve the semantic properties of symbols. A computer, then, according to Haugeland, is an interpreted automatic formal system. That is, a symbol manipulating machine. Tokens are manipulated automatically according to the rules. And then those tokens are going to be interpreted symbols, so that moves make sense, so to speak. Now, what an automatic formal system does first and foremost is to take care of the syntax, and the semantics takes care of itself automatically. In this way, a computer, as Haugeland says, is a semantic engine driven by a syntactic engine. Okay, let's stop here. Bye.